we will be continuing our discussion on the response spectrum. Okay. And the first thing is that we have told you that all the structures we will be used it as a single degree of freedom structures, right? So that means it can only have a one directions of motions. So it's a single degree of freedom. So we assume that structures are single degree of freedom, and we will be analyze this response spectrum based on the. Okay. So our work today will be the derive this SDF oscillator type of response and to a earthquake motions and see how does it gives us the mathematical form and what's the interpretation of this type of response. Okay, so so we are trying to understand the main purpose of this analysis, response analysis, is the how a earthquake gives the impact to a structure, and how do we understand what is the impact of this earthquake on that structure. So that means the response of the structure we try to understand. Okay, so as I said to you last time that that the structure as a first approximation for the response of to an earthquake. That is what we were trying to do. And the basis of this response spectra is basically the key concept of earthquake resistance design. So all our earthquake resistance design things, and also our prediction equation currently we use for the earthquake hazard, these are all based on the response spectra analysis, right? So we will be, therefore, this response spectra calculation is therefore one of the important things for our structural response analysis. Okay, so let's see. We have a Earth, and this is our structure, which we always talk about a lumped mass model. So this is your mass, and this is your spring things, and lumped mass model. So Earth will be vibrating with the earthquake things, and that we call it as a UG double dot, or might be the ground acceleration. G stands for the ground, right? And as a result, this mass will oscillate, and so it's earlier it was at a y distance, so now it is a y0. So there is a displacement u, which is the displacement of the mass. This will be equals to y minus of y0, right? So that's displacement, since it's a spring mass system. So this is basically we call it as an elastic system. So if it is an elastic system and there is a displacement of u, so therefore according to the Hooke's law, this force will be equals to k times of u, right? So u is the displacement. So this is the spring force. So spring force is equals to k into x. So this is k into u. So that's basically the Hooke's law formula, right? So if you see it in a cartoon, this cartoon is like this. So this is your mass, just like your cart, and this is your spring, and a force ut is acted on it, and that is basically make it an oscillate, right? Or the building vibrates. Or if you can see it in a mass type of model, so this is equals to your mass. This is the material of the body, and this is the u is the displacement it produced, and this have a length of L, And this k is basically E into I. So that means E is the L modulus and I is the inertia. So that can also be written like this way. So either of these things will be fine. Okay. So this is basically what we call it as the UT is the displacement, and it is a single degree of freedom vibrations, right? So as you can understand that this is the, if your earthquake comes, the building oscillates like this. So this is your oscillations or the displacement, and this is the function which we will be doing it in your multi-degree freedom things in later, but that's fine. So if you can see, this is your structure. So this is basically a multi-story structures like this, and on the top, there is a displacement is UT, because that is the maximum displacement. If there is a, if it is attached to the ground, then maximum displacement will be at the top, and these functions or these things we like to evaluate, right? So so UXT, that means at any height and any time, this thing is given by a functional form which is equals to phi x and ut. Phi x is the x dependent type of thing. So this x is on this side. So x dependent, and the ut is the time dependent, and this will be, this is called the normalized deformation, and that is phi L equals to 1. So the maximum, this will be taken it as a 1, and then we can find out all the other numbers, right? So we know our famous Newton's equation, F equals to ma. So F is the, because if there is a force, then there will be always a restoring force at the base of the buildings, right? So that equals to F equals to ma. So that M is the restoring force, which will try to keep the building in the position. So F equals to ma. So then A is the acceleration of the system it basically experience. So AT will be equals to, therefore, AUT dt square, or we call it as a U double dot T. So U double dot T, or the UT, U is always the building things, right? The ground movement is the UG. So that you should separate it out. So one is the building response due to the ground, but the ground acceleration is a UG, right? And this is what we are talking about, the only how the building vibrates having a mass m, and that's the things, right? So this AT is the building part. So if you see the force acting on the mass, so force equals to K into UT, right? And it is a restoring force. So that is why it is a minus sign. So this is the K into UT. So F equals to M U double dot T, and K into UT is the restoring force. So if you can bring it together, so then this will be the equations, right? And this equation, both the physics and the engineers are all very much they also know these things, because this is your differential equations we all need to solve in the math class, as well as in our all the one-dimensional equations. We have to solve these equations, right? So this is your this is the famous equation. So this is the second order differential equation with a m u double dot t plus k u t, and it's a homogeneous equation, and we know the solution of this equation, which is basically the displacement, will be the a when the cosine omega n into t, and b cosine sine omega n into t, and a and b at the boundary or the initial conditions. And initial condition is always the, at time t equals to 0, the x equals to x0. Okay, so t equals to 0, x equals to x0, and also the velocity, which is the x dot. This will be the x0 dot, right? So the initial velocity and initial displacement, that that will be used to calculate A and B. So, or you can write it in a complex form as a C into e to the power I omega n into t. Now, this omega n is basically, we can get it like this way, u dot t plus k by m into ut equals to 0, right? So this k by m is basically omega n square will be equals to the k by m, and this omega n is equals to square root of k by m, right? So this omega n is called the natural frequency of the structure, right? So, and this omega n is called the circular frequency. We call it as a circular frequency, and its unit is, what will be its unit? In radians per second. And if you can use this omega n will be equals to 2 pi of Fn, where the Fn is actually the frequency in cycles or the hertz, then the 2 pi Fn will be equals to k by m. So we all know Fn will be equals to 1 by 2 pi k by m. So that will be expressed as a hertz or the cycles, right? So omega n is k by m. So if we have a structure which has a mass is known and whose spring constant or the material property is known, so then we can calculate that structure's omega n very easily, right? So if you use that condition of the initial condition, then the initial time, the displacement is u0, and initial time, the velocity is v0, then ut will be equals to u0 cosine omega n into t, and v0 by omega n sine omega 0 into t. I do not like to calculate this one. I hope everybody know this equations, right? Okay, so that's the part. So this I have already explained, so that part is fine. So if you have a f equals to 1 hertz, I don't know why there is 1 hertz is come. But anyway, so f equals to 2 hertz, then this type of oscillations you will be expect from this part. Now, so in this example, whatever I had just formulated, that mathematical model, that mathematical model has no damping. So that means once it's set to vibrate, then it will go on vibrating, right? So it will not get stopped because there is no damping present. But in case of any real structure or any real bridge or any real things, they always have some damping. So the damping is must, because otherwise it will set into the motion and it will be moving. So we always introduce a damping in the system, and if it is some material, then it will always have some damping. So the damping part. So we have used the friction part, but we have not used the damping part. So we can use the friction form with basically the part of the damping system, and that damping is basically what we call as the damping force, and that damping force is equals to C into x dot, where the C is the damping constant, right? And it is proportional to the velocity of the body, right? So that is your damping force. And so if you can introduce that, then on this side, it was earlier Ku, then there is another force, which is the damping force, or the Cu dot is present here. So we have a reference model that this model will have a displacement of U, and from this side there is a damping force, and this is the friction force. They all come into these pictures, and then if you can show it, we will be showing the damping by putting a dashpot into the system. So this is what we call it as a dashpot in the system. So this is yours spring mass system, and this is the dashport system. And so F is equals to minus K into UT, and then this is the C into U dot. So that's why it is the F will be opposing these two forces in an equilibrium system. So MUT minus this part will be the Newton's second law. So our equation of motion will be now come to this form, right? So these things as when we can done in the same manner, U double dot T plus C by M into U dot into T plus K by M into UT, right? So that's our if we can do it like this way. Now, this C by M, this is the factor we can introduce a new number. C by M is equals to 2H omega N, right? So this is your 2H omega N. So this is your damping ratio part. So C by M equals to 2H omega N, right? So you can put it 2H omega N into U double dot T into omega N squared 0. So this is your damped system vibration, or the free vibration of a damped system. Then it will be like this. So H is called it's a critical damping of the system, right? So that's your equation. And this equation, if you finish your differential equation, and everybody knows that, so this differential equation has of the form of these things, right? So this things H squared minus 1, this will be, we call it is a damping frequency, right? So omega D, it's a damping frequency. This is the damping frequency. So please understand that there is a natural frequency of the structure, and then there is a damping frequency of the structure. And so the damping frequency and the natural frequency are related by this one, and this H is the damping ratio, right? The H is the damping ratio. And in general, if it is a concrete structure, this H value is around point, or we always take it as a 5% of the damping, right? So the 5% is the H value. So H will be equals to 0.05 that numbers, right? So that you can substitute in a place of H. So if you can see earlier you have seen that if there is a no damping, the vibrations will be like this way. It's a continue with the same amplitude as like this part. But as the damping is introduced, then it will have a decay, and that decay at that time, this time period will be 2 pi by omega D. Earlier, these things is equals to 2 pi by omega N, right? So that's your omega N, and now it is from here to here, this is 2 pi by omega D, because that's your damp period, okay? So if you plot, say suppose a 0.1% of damping, then when you can see that different damping values at the plot will be showing in a different way, right? So this is equals to H equals to 0.01, H equals to 0.02, and if it is a more damping, then it will start and then goes like this. If it is a less damping, when it will start oscillating, when it will have an oscillatory behavior. But if it is a highly damped system, the structure will be like this, and then it will be immediately stops, right? So now, so this is, so far, whatever we have discussed is basically the free vibration. So that means if it is set to vibrate, then it will go on vibrating. Either it will be without damping or with damping, right? Now we say that we are giving some external force. and try to make the vibration as a force vibrations, right? So then we will be expecting that when there is a movement on the earth, so that means earth is giving a ug into t, and as a result there is a vibration, and that vibration we like to do, and let us assume this is a damped system. Then what should be the equation? So F will be equals to minus K into U into Cu. That part is fine. So there is a F part means when there is a vibration of the system, so M into U double dot T plus the M into UGT. So that is the input motion on this one, and it will be opposed by the Ku and the Cu. That means the spring and the damping force, right? So if you can bring all together, then this will be our equation. So this is U double dot T minus plus C into U dot T plus K into U. C by M into K by M into UT. UT is equals to the your minus UG double dot, right? So that's the system, or that's the force vibration we are getting it, and then we can substitute the C value. So this will be equals to 2h omega n, and K by M equals to omega n square into this one. So that's our equation of motion to the structure when there is an earthquake, right? Now, so if you have this equation, now let us understand how to do these things, right? Now, so you believe that this is your natural frequency of the system, right? But you are giving an input, which is the ground motion, that has a frequency of omega. So the omega is the frequency of the ground motion. So don't get confused with the omega and omega n. So the omega n is basically for the building, omega is for the ground motions, right? So this also have a sinusoidal motion. For the time being, let us assume that this earthquake is also a sinusoidal waves. Okay, so UG, that means the ground displacement. UG is the ground displacement, equals to the UG 0 and exponential I omega t. So that's your ground displacement value. So that's your maximum things is basically UG 0. So this is equals to UG 0, and you can write it like this way. So it can be shown by the substituting on this equation. If you can substitute in this equation and simplify it, then UT will be equals to U0 into exponential of I omega nt, because that's your building displacement. So this is the building response. We call it as a building response, or sometimes we call it as a deformation response. So this is the building part, right? So this is the deformation response of the building. We come to that term afterwards. But let's see, this is your displacement of the building displacement will be equals to peak values of the building displacement U0, peak value of the building displacement U0 and exponential I omega n into t, because the building is vibrate with your omega nt. So if you can divide these peak values, so that means U0 divided by UG0, so that means building response, but the peak building response normalized or part ground peak things, then this value will be equals to this way, right? So just to substitute there and calculate it, it will be these equations. Right? And this equation is you have already learned also in your vibration chapters in physics and also in many contexts. So I understand that this thing is known to you. So and so the amplitude of the the building, the maximum amplitude of the building for a given maximum amplitude for this one, you can calculate, provided you know the frequency of the earthquake and also the natural frequency of this one. So this is the ratio, and if it is the phase, what will be the phase value? So the phase will be equals to 2h omega n and this number, right? So this is the amplitude at the different damping values. So if it is a less damping, the amplitude will be very high. If it is a more damping, the amplitude will not be oscillatory, right? So similarly for the phase, we can have a different response. So that's the phase values, right? So so we have found out that how for a ground response or a ground vibration, how the building will respond. Okay. Now, so now a interesting case is this, that if the omega is very, very less than omega n, so that means the natural frequency of the building is very less and the ground vibrating frequency is very high, right? Omega is very higher than the omega n. So, so what will happen then? Right. Then omega n, if it is a very small, then the building will not respond at all, right? So the U0 is more or less 0. Okay. So U0 is more or less 0. So so that means essentially that the oscillator will approximately track the input motion. So that means if it is an oscillator, it will be basically moving with the ground. So it will basically follow the ground motions because it has its own displacement, right? And the phase in that case will be equals to t equals to 0. So this is the case if it is a omega is very, very less than omega n, right? If omega is very, very greater than omega n, so that means the ground frequency is very high frequency ground motion, and then the building things. So U0 will be approaches to UG when it G0. So that means the ground part will be equals to this way, right? So so the phi is equals to pi. If you can put that number, so then phi will be equals to pi. And if it is a omega is equals to omega n, so that means if the ground things are at the same as the building frequency, then what will happen? See, then the building will be on set to a resonance, right? So if the building set to a resonance, so that means the building oscillations will be much higher, okay, and it will be a tremendously vibrating body, and which as an engineer or as a designer, we all want to avoid that situation. So we should not design a building which has its own natural frequency is same as the frequency of the expected frequency of the earthquake in that region. Because if you said that, then it will be devastation, right? So so in that case, the phi will be equals to pi by 2. If you can put that equation there, then the building will be like this, right? So that's your three cases or three extreme cases. When omega is very, very less than omega n, omega is greater than omega n, and omega n equals to 0. So now my question is that if I have a any input to the acceleration to that building, how the building will respond, right? So we have seen that u0, so the peak value, we have calculated the numbers, but we like to understand that if there is any building response or any ground response, let's see that is your acceleration of the ground, then how the building will respond in that case, right? So this is what we call it as a special integral. It is called Duhamel's integral. Now, what this integral will do, this integral will calculate that whatever is the ground acceleration or the ground motion, that means this is basically UG double dot T. So that means this is the ground motion. If you know this motion, then you can calculate whatever the response of the building. So this is your building response. So this is basically the damping part of the system. And then this is your sine part, and this is your exponential part. And please see this one. This one is t minus tau, and this one is also t minus tau. And this integral carried over the d tau part. So tau becomes from 0 to infinity, right? So this integral is basically a convolution integral. Okay, so this is your convolution integral. So that means we are convolving the ground motion with the response of a building response for a unit impulse, right? So that is what we try to do. So let's see, if we assume that the acceleration is just like a pulse, or the delta pulse, or this one. So AT will be equals to delta t, right? So then the result will be that this ut will be equals to AT is only delta t. So then this will be equals to ht into this part into sine omega t into all these numbers, right? So that's your unit impulse. This will be the response, and that is the building response, right? So for the structure response will be the ut for a delta t type of things. Now, if we give a Heaviside step function, say suppose like this, when ht equals to 0, then all of a sudden the acceleration value comes here, and then that will be equals to 1. If you see that, that's a Heaviside function, then the functions will be looks like in this way. There will be some response, and if you can see that this is your a tau into ht tau into this number, and then this is all these values, right? So that's a response for the for any types of ground. If you have any types of ground motion, then you can calculate it like this way. So this is what we call it as a method of convolution, that ht equals to always ft into gt, and that can be, so this is what we call it as a convolution operation. And I think everybody in geophysics, they all know these convolutions, right? You know this, right? The convolution things. So this is your f tau into g into t tau, and this integral, and these things are being carried over the tau part. So if we have any filter or anything, this is basically a convolution operations, right? So this is our f0 at 1, f1 as a 1, and f2 as a half. So this is our, let's see that this is our filter, and so this filter is here, and let's see, this is our signal, 1, half, and half. So we will be just folding it, and then we can make these things as a front like this way, back like this way, and then we can shift it each one unit, so that will be equals to H0 equals to 1, then H will be equals to this one, and I think then the output will be equals to this. So if you have a filter which have a input of 1, -1, 2, 1, -1, and -1.5, and if you give the input as a input function as a 1, half, and -half, if you give this as an input, then your output will be this one, right? So that will be the output. So similarly, your input here will be the ground acceleration. So the input here will be the ground acceleration, and the system response or the building response will be equals to the sine omega n into this thing into e to the power minus omega n into h into t minus tau. Then you can do this integral, and then you can calculate these numbers, right? So I had some dot for the so this is one, the pulse would be convolved with this one, and then output will be like this. So this pulse will be convolved with this one, the output will be like this. So suppose this is a convolved with this one, then the output will be like this, and so on and so forth. So we'll count some of the things in the source modeling later. So so in structure, we have something around 0.01, 0.2, 0.5. So the 0.05. So these are the damping we usually used. And so that damping values we can take. See, suppose if this is your ground original response, and then we have a use for a different damping values, and for a particular frequency of 5 Hz, then this is your ground response. So this is your ground acceleration, or it is called UG, right? So UG double dot T, this is the ground acceleration, and you will be seeing a UT for different damping values, right? So these are the different damping values for a fixed FN. So you can calculate different building response UT at a different damping for a different frequency. And similarly, if you can say the same damping but a different frequency, you will be also getting the similar response. So that means this is basically what we are trying to do. I had fixed the damping value. Let's see, damping is equals to 5% of the critical damping, 5% of critical damping. So we need to know that 5% of critical damping. So this value is known, and then we will be set the omega n can go from, say, 0 to some numbers. Let's see, or might be the seismologists are very much comfortable by giving the omega n, but the engineers are comfortable with giving you the time or the Tn, which is a 2 pi by omega n, right? So that's basically the engineers like to give is a period. So we can start from a very low period, 0.04 to, say, suppose 15 second type of period. So 0.04 second to the 15 second. So this omega n will be varying from 0.04 to 15 second, and the damping will be fixed at a, say, suppose 0.05, and we will be getting the time value here, and carry out this integration with a different steps. So this tau is the step on which the sample data, right? So that is a sample data, say, with a different 0.05 interval. So we will be integrating it and compute the the building response, right? UT. So this is the same thing. I am showing it here that for a particular damping, for a particular frequency, we are plotting the UT response, right? So this is also from this one. This is at a different frequency, but the same damping, and so on and so forth, right? So this UT is basically our interest to find it out. So that is your what you call it as a building deformation response. So that means how much is the building deformed, right? So deformation response is basically the UT. Okay, so now if you can see that this is your UT value, and at a particular damping and a particular particular period and particular damping, that will be the U values, right? And so this is your time history. So that means this will be the same time as the time of the earthquake or the time of the things, because that is your U tau, UT on the outside. So this is UT is basically same will be the tau value, because this will be calculated for the entire time thing. So that will be the UT. So this is your T, and it is your U function, and we calculate the maximum value for each Tn and each damping, right? Each Tn and each damping, we calculate maximum of this one. Okay, we calculate the maximum of this one, and that is your U0, right? So we try to calculate the for a given damping and for a given frequency, we take let's to calculate a maximum response or the peak response of the building, right? Let me see. So that peak response is called the spectral displacement. So that is the peak response of the building, right? So that means that is the maximum of T for a given T, for a given tau n, a Tn, and the given damping. We calculate the SD for this one, and so we changes the frequency or the period, whatever it might be. So we can plot it with a different period for the same damping. So H is fixed, and for same damping, we are plotting the U0 value. So that is what you call it as a SD, or we call it as a spectral displacement. This is called spectral displacement. So please understand, this displacement is not the ground displacement. It is the displacement in the building side. Okay, so the building is responding, and that is spectral displacement, and that value we like to plot. Okay, so this is your, or you call it as a displacement response spectra, right? So this is your spectral displacement or the displacement response spectra, and that is equals to the SD. So SD will be a function of either, when SD is basically calculated from the maximum value obtained from each frequencies, right, and each damping. So now if you can see our previous equation, that where you say that U double dot T plus 2 T plus omega nt equals to this ground motions things. So if your omega n, that is natural frequency, is very small, okay, so if it is almost close to 0, then then this part will be all 0, right? So then U double dot T equals to minus UGT. So that means acceleration is equals to the ground acceleration, but in a opposite direction. So basically, at low frequency, if you just integrate it, then UT will be equals to UGT. So So in that case, ut will be equals to ugt. So that means the response of the building will be the same as whatever the displacement of the ground, right? Now, if it is if the omega n is very large, if the omega n is very large, so then omega n square into x will be equals to, if it is a displacement, so then that will be equals to omega n will be equals to minus z, because this value is predominant, and then it will be basically so the high frequency SD is asymptotic to the peak acceleration of the ground, right? So at high frequency, this will be like this way. So if you can see it, if it is a very steep structure, that means structure is very steep, so it will not move at all. So if you give a UG, since the structure is very steep, if you give a UG, it will move. Well, if the ground acceleration UG double dot, then it will move the same value as a UG, because the structure will not, the ground will not able to move the things because it's a very steep structure. But if it is a very flexible structure, so that means if there is a ground things, then it will be flexible like this. So then it will be, you can see that this is your UG, but this part, it's basically the zero. So UG double dot is basically equals to some x into UGX. So this will be equals to the omega n equals to, this omega n is equals to 0. So that means it's a very flexible structure. So if the omega n part you like to do, so if it is a omega n part, then this side is for a flexible structure, flexible things. So you go to the stiff side, right? So if you plot it with your omega n, but if you plot it with a Tn, then the Tn equals to 0, that means it's a very stiff structure, and this will be very flexible structure. So your total displacement, if you can say the total displacement, please understand also this one. Your total displacement is basically the displacement produced by the ground plus the displacement produced by the structure itself, right? So that is your U total, this one. So UG, or we can write it like this way, UGT and UT. So this will be equals to UGT and plus UT, right? So these are the two. This part is the total displacement, and if it is a so that means that is your spectral displacement, or UG. So you can calculate. So that means if you know this is your spectral displacement of the body, you can calculate. But if you need to calculate the velocity response of the system, so velocity response of the system, or we call it as a pseudo velocity response, PSV. So PSV, why it is a pseudo? Because this is not the response of the entirely the ground. It is the response of the building. So therefore, let me iron it out. SV will be equals to right. So if your ground, if your structure has a UT equals to sine omega nt is the form, then U dot T will be equals to the omega n into cosine omega n into T, right? Now, seismogram is not, so the explanation, it will be that it will be the omega n into some sort of a displacement part, or the cosinusoid displacement part. So that is your velocity. So we call it as a pseudo velocity, which is the omega n into SD, right? So we recognize that this PSV will be equals to SV. So both will be the same if it is a omega n is very so if it is a omega n is a very small value, then these things will be equals to the omega n into SD, right? So that will be equals to our SV values, right? So PSV equals to omega n into SD. So how do we calculate that? So we calculate U0 as a maximum value of whatever we get it from a particular T, particular tau n, particular H value, you give that and calculate your U0, right? For each time period, right? And then vary the Tn value only and calculate different U0 at different Tn values, right? So this is your different Tn values, and then you plot these Tn and Un values, right? So you can plot Tn versus your U0 values, right? So that will be your spectral displacement, right? After you calculate this one, you take your Tn means SA 2 pi omega n. So you can calculate this PSV will be, and that will be equals to your SD. So you take that SD value and multiply with a omega n. So that will be equals to the pseudo relative velocity response, or we call it as an PSV, right? Now, so PSV and SV will be differentiable or differentiable at a very high frequency, but at a normal frequency they are always the same. So we do not care about the PSV and SV very big separation in terms of the engineering part, but actually there is a difference, right? Now, if you calculate the PSA, which is basically omega n squared into SD, right? So that's your, so that means PSA equals to, so this is a pseudo acceleration part. So this is actually, we call it as a pseudo spectral acceleration. Pseudo spectral acceleration. So this is the PSA. So if you know the SD and multiply your omega n square with that SD value, so that will be a PSA. So since the SD at a different frequency, so the PSA we can also plot at a different frequencies, right? So this, so we have a three spectra, therefore, SD, PSV, and your PSA, right? So these three spectra we can plot them against the omega n or Tn, right? The seismologist preferred the omega n, the structural engineer prefers the Tn values. So this is your PSV plot. Now, let's see for your ground motion, peak acceleration is equals to 0.1 g. Let's see one ground accelerations, peak accelerations comes at the 0.01 g, and peak displacement from the ground acceleration just we have calculated last time. Let's see, it's the 0.03, right? So we also need to understand that there is another response. It is called absolute acceleration response, and we call it as a SA. So SA and PSA, there is a difference, right? So that difference we need to recognize. So that means you have calculated U double dot T and UGT. It is the total displacement of the system, right? And that will be equals to U double dot T equals to 2H omega n into U dot T minus UGT equals to minus omega n into these two, right? So that that you can calculate by bringing this side and this part or this side. So basically, this will be like this, right? So let's see. Again, what was it? Okay. So the spectral acceleration is basically the maximum of you calculate UT, whatever is the absolute value, and UGT, whatever is the absolute values. So that will be the spectral accelerations, right? So spectral acceleration and PSA, pseudo-spectral acceleration, which is the omega n square into SD. So that is two different parts. So here it is basically you are using this part only, and this part you have to add in order to calculate the SA values, right? So we are basically get 5 names. SD is the relative displacement, SV is the maximum relative velocity response, PSV is omega n into SD, and PSA is equals to omega n square SD. So that is your PSV and PSA values, and the SA is the maximum absolute response spectra, which is the maximum of these two, right? So so these are the response spectra we need to plot and we need to analyze. So entire structure property can be understood during a time of the earthquake, how the structure will behave if I know the structures, the response spectra of the ground motions. Now,